if an electron transits from third shell to first shell, that time how much energy is going to emit? This we can find. We will calculate energy of third shell of hydrogen atom, which will be equal to minus 13.6 into Z for hydrogen atom will be 1 square upon N, third shell it is coming from, it will be 3 square. Electron volts per atom. If electron is coming up to second shell, from third to second suppose it comes when transition is made, it is called de-excitation, then energy of second shell will be minus 13.6 into Z will remain 1 only upon 2 square. Now difference of energy in these two comes out to be E3 minus E2, which can be given as equal to delta E, and this will be equal to minus 13.6. This is energy of electron in third shell. So minus 13.6 into 1 square upon 3 square minus of minus, we get here 13.6 into 1 square upon 2 square. Right. Now as you can see that this energy will come out to be positive in electron volts per atom. This will be calculated. Actually we can simplify this formula by simply using that energy emitted or absorbed as equal to 13.6 into Z square into 1 by N1 square minus 1 by N2 square, and again this energy will be in electron volts per atom only. Remember one thing, this formula can be used to calculate energy emitted or absorbed both. If electron goes from lower level to higher level, at that time energy, the difference amount of energy will be absorbed. If electron comes from some higher level to lower level, at that time the difference amount of energy will be given out by the electron. Now, the thing is that remember one thing while using this formula, that N1 always has got to be the lower level and N2 always has got to be the higher level. Then this will give you the amount of energy which will be absorbed at the time of excitation from N1 to N2, or the energy released which will be given out at the time of de-excitation from N2 to N1. Right. Now, sometimes questions come like this also, that calculate the wavelength of a radiation which can excite the electron from this shell to this shell. In that case, what you have to do? Simple again. This is energy which needs to be given to the electron if electron has to transit from N1 to N2. Now, we use Planck's concept which says that delta E is equal to hc by lambda. So, you use this formula hc by lambda equal to 13.6 into Z square 1 by N1 square minus 1 by N2 square electron volts per atom. If directly we want to calculate wavelength of the radiation emitted or absorbed, it becomes 1 by lambda equal to RH Z square into 1 by N1 square minus 1 by N2 square. Here RH is known as Rydberg constant. It is written like this. Some call it Rydberg constant also, whatever you want you can call it. So it's called Rydberg constant here, and its value is given. Simplest way of remembering is 109678 centimeter inverse. That's the best way of remembering the value of Rydberg constant. Right. So directly, if it is asked that calculate a radiation of what wavelength will be emitted when electron transits from fourth shell to first shell, then very simply we can give it as R1 by lambda equal to RH Z square. Z, suppose it is hydrogen atom, then Z will be 1. Here N1, in this case electron is coming to first shell, so N1 will be 1 here. N2 coming from fourth shell, so N2 will be 4 here. So simply substitute the values, you get the answer. Answer comes in centimeters. Here value of lambda will come out in centimeters here. Right. Now hydrogen spectrum will be discussed here somewhat. The spectrum, first of all the spectrum was discovered for hydrogen, and what they found, actually first of all it was discovered by scientist Balmer, by the name Balmer, and he saw certain lines in the spectrum, and those lines after his name only are called as Balmer lines here. What happens here, that if electron de-excites from second shell up to first shell, right, or from any other shell actually up to second shell if it de-excites, from any higher shell up to second shell, from fourth shell to second shell, third shell to second shell, any higher shell up to second shell if electron de-excites, then the line emitted is called to be having in the Balmer series. We say the line is in Balmer series here. Means from any higher shell up to second shell, if electron de-excites, we call it as Balmer series. How the wavelength of a particular line in Balmer series can be calculated? This is done by using 1 by lambda equal to RH Z square into 1 by N1, in this case will be 2. Because the lower level will always be 2, because the electron had to de-excite up to second shell only. So it becomes 2 square minus 1 by any higher shell it may be. So this is N square here. This actually was the first one, not to be discovered, not the first one actually. The first series which we get in lines in is Lyman series. But this was discovered later. The reason also I'll tell you. The reason for this was that Balmer series lines are found in visible region, so we can see them. But Lyman series actually is not possible to be seen. That's why they were discovered later on. Lyman series similar, exactly similar from any higher shell. If they come up to first shell, then we say that the lines fall in Lyman series. Formula similarly will become that 1 by lambda equal to RH Z square into 1 by 1 square minus 1 by N square. N again may be any higher shell, somewhat less than infinite. So up to any shell, they de-excite up to first shell, then we say that the lines fall in Lyman series. Similarly, after Lyman Balmer, we have got Paschen series. Paschen series. Similarly, in this case, only this value is going to change from any higher shell if electron de-excites up to third shell. Then we say the lines fall in Paschen series. Then we have bracket series. Exactly in similar manner, this comes up to fourth shell. Then we have Freund series, and this obviously will be up to fifth level, from any higher shell up to fifth level. Only difference is here that the value of N1, which is the lower shell with the lower level, keeps on changing here. Higher level which obviously will be same. From any higher level to up to this level it comes. So we get Lyman, Balmer, Paschen, bracket, Freund. Right now. So this is hydrogen spectrum. This was the spectrum which could be explained on the basis of Bohr's model perfectly. If he said that, okay, if electron is de-exciting from fourth shell up to first shell, and we will get a wavelength of this much particular wavelength, this much particular angstroms, exactly based upon calculation, the wavelength was found to be present on that perfect line. So he was excellent in explaining this. But as usual, this model also could not survive for long. And what happened after that, certain observations were done which made it to fail. One of the reasons for the failure of Bohr was its advantage only, that Bohr could tell everything. It could tell the energy, it could tell the radius, it could tell even the velocity of the electron. This only became the problem. That time only what happened, one scientist by the name Heisenberg came. And Heisenberg said that it is impossible to measure the velocity and position of an electron or a subatomic particle simultaneously and precisely. He said it is perfectly impossible. You can never measure the velocity and distance or the position of the electron precisely and simultaneously. But Bohr did the same thing. He found the velocity as well as the distance from the nucleus of the electron perfectly and precisely. Bohr says that if electron is present in the first shell of hydrogen atom, this is the nucleus here we assume, if electron is present here, Bohr could tell both the things. He told that if electron is in the first shell of hydrogen atom, then this will be exactly at 0.529 angstrom distance from the nucleus, and this would have been moving with a speed of 2.18 into 10 to power 6 meter per second velocity. So both the things could be told by Bohr perfectly and precisely, simultaneously and precisely. which according to Heisenberg uncertainty principle is impossible. Actually, Heisenberg, we cannot say that this might be wrong. Why? Because this is a principle. It has been derived perfectly mathematically. So there is no mistake in this which can be agreed that no, Bohr is correct, Heisenberg is wrong. That's not possible. This became a blow for Bohr's model. Second thing which Bohr could not explain was splitting of lines. Later on it was found that if the spectra of hydrogen or any other multi-electron system was taken in a magnetic or electric field, lines used to split. This effect was known as Zeeman effect or Stark effect. Two effects. One was called Zeeman effect. Other one was called Stark effect. Stark effect. These two effects could not be explained by Bohr again. Third thing, Bohr's model used to fail to explain the spectra of multi-electron system. Other thing, Bohr considered electron to be only a particle. He assumed it to be only a particle, nothing else. While de Broglie said that electron can behave both as a wave as well as a particle. So he did not consider dual nature of electron, he considered only particle nature of the electron, which again became a problem for Bohr. Now, we'll discuss first de Broglie here. After that, we come to Heisenberg. See.